2 tells us to evaluate, and they give us over some curve, we have a 2xy dx plus x squared z dy plus an x squared y dz. Okay, and we're going to evaluate this over the curve given by c of t equals t squared, comma, sine pi t over 4, comma, e to the t squared minus 2t, close arrow bracket. Okay, where t stays in between 0 and 2. Okay, so upon first looking at this, doing it the mechanical way, or the technical way of the whole like f of c of t dotted with c prime of t dt in our integral, that would be absolutely awful with this c of t. Okay, so this is awful. I just want to stress that. So what we're going to do when anything in life seems really awful and intimidating, we are going to look for shortcuts. Yes. And this is not an exercise of laziness. This is an exercise of resourcefulness. Okay? So we're going to be resourceful and draw upon what we know. Okay? And any theorems that might pop up. So that's good as well. Theorems are always helpful because they're basically shortcuts to some things. Okay? So let's try to find out if our f is so our vector field is conservative. Okay, so basically what this is, this in front of the dx, that's going to be our f1. So I'll draw a line down here. So this is f1. X squared z, everything in front of the dy is f sub 2, and the last one, x squared y, is f3. So f1, if it's conservative, if the vector field is conservative, this should equal partial v partial x. f2 should equal partial v partial y. And the last one should equal partial v partial z. So let's see if we can find a potential function, potential function for our given vector field. So if we have partial v partial x, and we set that equal to 2xyz, and we integrate with respect to x, let's see what we get. So we're going to get some candidate function. So this will be x squared yz, whew, that was a weird z, plus some function of y and z alone. Okay, so this is one of the potential ones. And then we have, let's try the second component. So we're going to set those equal to each other, like that. And then we'll integrate with respect to y, So here we get another candidate function, and this is going to be x squared zy plus some function of x and z alone. So this is another candidate one. And the final one, I'll put it down here. So we're going to compare partial v partial z with x squared y. So we're going to integrate with respect to z on both sides. And we get another candidate function, which is then x squared y times z plus some function of x and y alone. So these are our three candidate functions. So let's go shopping and see what we actually need from each of them. So our final function should include, let's look at the first one, some term like this, x squared yz. Okay, and then we'll see if we need this later on. Let's jump to the next one. So looking at this term, x squared zy. So we already have something like that here, so we don't need a duplicate. Okay, let's look at the third one. We have x squared yz. Again, we don't need a duplicate or a triplicate. So we're done, basically, and we don't need these at all. Okay, so this is it, and then you could always add in the plus c. But that's not necessary. So this is our potential function. So since we found a potential function, that implies that our f to begin with was a conservative vector field. So f is conservative. conservative. Okay? So that already is a very big help. That's really good news because then we can apply the fundamental theorem for conservative vector fields. So I'll continue this on the next slide. So we have our v of x, y, z that we found, our scalar potential function, which is given by the following, x squared y, z. Okay? So given what we had, so this is what we started off with, was 2x, y, z, dx plus an x squared z dy plus x squared y dz. So this is going to be equal to v of q, which is v of the ending point. So right now I'll just write v of endpoint, okay, minus v of start point, start point. Right, and where v is this thing, so v is our potential function, okay. All right, so now we need to figure out is our endpoint and our start point. So going back to our parameterization for the curve that we were given, so this is what it looked like, was c of t is equal to t squared, comma, sine t times pi over 4, oh, sorry, that's supposed to be a 4, and then e raised to the t squared minus 2t, all right, and t ranged from 0 to 2, okay, so the beginning of our curve can be found by finding c of 0, so we're just going to plug in 0 wherever you see a t. So we're going to evaluate this at 0, so we have 0 squared, and then sine of 0, and then e to the 0 squared minus 2, 0. Okay, so this is going to turn out to be 0 and a 0, and e to the 0, which is a 1. So that is our start point. So this is the start. So you can kind of consider that like p, right? You know how this is like q and this is like p. Okay. So now for our endpoint, we just take the ending value of t and plug it in. So that would be c of 2. So then in this case, that would be 2 squared. And then we plug it in here, so that would be 2 pi over 4. Okay? And then we have e to the 2 squared minus 2 times 2. So this is going to be a 4. And then a sine pi over 2 is 1. And e to the 0 again is a 1. So this is our ending point, so this is like our q, end. And p is start. Okay, so now that we have this, we're going to take it and plug them in. So we have v of c of c of 2, because this gives us our endpoint, minus v of c of 0. So now we have our actual points, so we can plug them in, and we get 0, 0. Sorry, I keep writing that one first. So our endpoint, that's what we start with. So this is our endpoint, so we start with 4, 1, 1, minus v of 0, 0, 1. All right, so I'll continue this on the next slide. So our v of 4, 1, 1, this is basically our x, y, and z, right? So then when we plug that in, we get x squared, so 4 squared times y, 1, times z, 1. So this will be 16. And our v of 0, 0, 1, x, y, z, this is just going to be 0 squared times another 0 times 1, which is 0. So finally, what we're going to get is v of 4, 1, 1 minus v of 0, 0, 1 is going to equal 16 minus a 0, which ultimately equals 16. Okay, so that's the answer for our vector line integral that we had to compute. All right, so the last question, number 3, says, let f equal the following. That was a weird arrow bracket. Negative y over x squared plus y squared, comma, x over x squared plus y squared. Okay, so we're going to let f equal that. So this is our vector field, and we're going to, the next part is determine, so here's the meat of it, determine the line integral, so f dot t ds, or if you think of it like this, f dot ds arrow. So we're going to determine the line integral, basically, of the following curves. And I have 4 curves that I'm going to show you. But basically, so what we have here, well, I guess I'll identify it after. But here are curves, first of all. So we have a curve here. So this is going to go from here, around, and come back. Okay, so it's going this way. Alright, so that's our first one. Here's our second one. We're going to have something like that. Okay, this time it's going the opposite way. And then we'll have something that looks like this. So we have something here, then it goes in and comes back around. Okay, something like that. And we're going to go this way. We're going to travel the curve. Alright, and then our last one's going to look like this. Alright, so something like that. Okay, so first of all, whenever we're looking at something like this vector field should pop out as the vortex vector field. You should recognize this. It is important. And so this is the special case. So special. Because as you can see, all 4 examples here that I've drawn are closed curves, right? Because the start and the end point are the same. Okay, and the start point doesn't even have to be there. I could make it here, and it would still be a closed curve, right? Because it encloses an area. But anyways, so normally for a conservative vector field, when it is closed, so the circulation around a closed curve, when your vector field is conservative, should be 0, right? That was one of the fundamental theorems of conservative vector fields. However, vortex vector field is special, so it is an exception, remember? So anyways, the way you calculate the line integral is how many times, when you traverse the curve once, all the way around, how many times did you go around the origin, okay? So let's look at this first case here. So we have the origins there, and we're starting here. So we go around, 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 and you always have to follow the direction of the arrows, or the direction they tell you in the problem, right? And we end up here. So we went around the origin once. So that means that corresponds to a winding number, n, of 1, okay? So that means that our line integral is equal to 2 pi times 1, which is just 2 pi. So it's going to be 2 pi for this one. And let's look at the second one. So here, this is a little bit different, because we're going to start here and follow the arrows, so we're going down instead first. So we're going in the clockwise direction, and then we end up where we started. So in this case, it's actually going to be the reverse, because we're traversing it in the opposite way. So this will be a negative times, well, I guess I'll just put, it's negative times the line integral going in the counterclockwise direction, which is normally seen as positive. But anyways, the whole point behind that is saying that we're going to have a negative sign stuck in front here. So that'll be a negative 2 pi. Also, just as a side note, because it came into question here, it's relevant. So the traditional orientation, so this means the direction that you travel on your curve. Orientation is traditionally seen as counterclockwise is positive and clockwise is negative, unless they tell you otherwise. Unless they say that in the problem, like, the curve is traversed in the clockwise direction, and that's its orientation, then that would be your positive one, okay? But traditionally, if they don't tell you, counterclockwise is positive, so going opposite 2 o'clock is positive, and going in the direction of like the hand of a clock, that would be negative. Okay, so in this case, this was negative, all right, because they didn't tell us any background information about it. Okay, so now let's look at example 3. So we're starting here, and we go around, follow the arrow, so we're going around, okay, and here I want to stop. Even though we haven't made it all the way around, what I've just completed was a full 360, right? So I've gone around the origin, here's the origin, so I went around it once. So this is like 0, pi over 2, pi, 3 pi over 2, 2 pi. So I already gathered up 2 pi in my angle, right? So then I keep going. I'm not done with my curve yet. And then I get to this point. I get back to the start. So by this time, I've actually gone around the origin 2 times, 2 full times. So that means that I'm going to have 2 pi times the winding number, which is 2. Winding number is just how many times you circle the origin. So on this one, it'll be a total of 4 pi. Okay? And this last one, this is kind of the, not a dumb one, but it's just kind of fun. So this one, let's see, when we go around the curve, okay, we're going around, all right, we're passing the origin, but we're not going around it really, and we get back to where we started without even going on the other side of the origin. So in this case, the winding number is 0, so that means 2 pi times 0, so that will be 0. Okay, so that does it for the practice problems here. Good luck on your homework, and I'll talk to you in the next video if you watch.